right, so today, the big question we're going to start with is, as we're rotating the coordinate system, and we're looking at this material point through the lens of different orientations, at what angle of rotation are we going to maximize or minimize our sigma x prime value? If we have an equation that describes sigma x prime, such as that one, if I have that equation and I want to know at what value of theta is this equation maximized or minimized, how do I determine that? Thank you. That's why you took calculus. Thank you. You're going to take a derivative of this equation. When that derivative equals 0, we will know we're at a point of maximum or minimum magnitude of the function. So we can take the derivative of sigma x prime with respect to theta. And if we do that, we should get sigma x minus sigma y over 2. So first of all, let me just say the first term goes away completely, right? The first term in the equation was simply the average of the two normal stresses. It didn't involve theta. So when we take the derivative of that, it becomes 0. So now we're working on that second term. We have this constant out in front that is sigma x minus sigma y over 2. And then we take the derivative of that trigonometry term, and we should get negative 2 sine 2 theta. The derivative of cosine 2 theta is negative 2 sine 2 theta. Plus the last term, tau xy. Now we're taking the derivative of sine 2 theta. So that gives us 2 cosine 2 theta. And this all has to equal 0. And from this, we can determine that the tangent of 2 theta is equal to tau xy divided by sigma x minus sigma y over 2. Or I can take that 2 and put it up top and say 2 tau xy divided by sigma x minus sigma y is equal to tangent of 2 theta. And if I want to solve for theta, that then becomes 1/2 the inverse tangent of 2 tau xy over sigma x minus sigma y. And this value of theta that gets us to our maximum value of sigma x prime has a very special name. It's what we call our principal angle. So I'm going to put a sub p. We call it that because it's the angle of rotation. It's how much we have to rotate our coordinate axes to get to what we call the principal plane, which is where our maximum sigma x prime acts.
How did you get the tangent of 2 theta?
I divided, let's see, so I put one of these on each side of the equal sign. So, all right, so this term equal to that term, move it over, and then I divide that cosine term and I divide the sigma terms, and then the sine over cosine becomes tangent. So this is how much we need to rotate when we're given a certain stress state in the xy plane with respect to the x and y coordinate axes. If we rotate the axes by this angle, we're going to get to the principal plane, and this principal plane is where our normal stresses are maximized and minimized. And we call this our principal plane. So this is extremely important because when you're designing a member, you're not interested in some arbitrary X and Y stress values. What you're interested in is what are the maximum stress values that that material is going to see, because those maximums are going to be what is going to cause that material to fail. So now that we know where the plane is oriented, the next major question is, what are the magnitudes of these stresses on this plane? So to do that, we can plug in theta p, but theta p is kind of ugly. Would you agree? I don't really want to plug that into an equation that's already 3 terms long and I have to take the sine and cosine of theta. So instead, I'm going to do this little trick on the next slide to make our lives a little bit simpler. If you don't like my trick, that's fine. You can just plug in 1/2 inverse tangent of that thing. Cool. All right, so my trick is going to be looking at this definition here. I know that the tangent of some angle that I'm calling 2 theta is tau xy over this difference over 2, right? So on the next slide, I'm going to draw a triangle. I'm going to label this angle 2 theta, and I'm going to call that side r. So I said the tangent of 2 theta is tau xy over sigma x minus sigma y over 2. So would you agree that that triangle says the same thing? The tangent of that angle is opposite over adjacent, which is tau xy over the difference of my normal stresses over 2. Cool. So now I can calculate what that hypotenuse has to be in terms of these stress values. It has to be sigma x minus sigma y over 2 quantity squared plus tau xy quantity squared. And I can calculate cosine of 2 theta. Cosine of 2 theta is going to be adjacent over hypotenuse. So sigma x minus sigma y over 2r, where r is that thing in the radical. And sine of 2 theta is tau xy over r. That's opposite over hypotenuse. So now as long as we can use r instead of that radical, we have something that's a little bit cleaner to put into our equation. Okay, so now we're going to plug in to our equations for sigma x prime and sigma y prime and tau x prime y prime. So sigma x prime, sigma x plus sigma y over 2 plus sigma x minus sigma y over 2. Now it's supposed to be times the cosine of theta, but instead of the cosine of theta, I'm going to plug in this right here. So then this is going to become sigma x minus sigma y over 2r. Now minus tau xy times the sine of 2 theta, which we said was tau xy over r. Okay. This first term is just the average stress. Right? Sigma x plus sigma y over 2 is the average stress. Plus, look really closely at what's left. I have an sigma x minus sigma y over 2 quantity squared minus a tau xy squared, and that whole thing is over R. If we flip back, did I say minus? This should be plus. I don't know why I have a minus there. Plus tau x squared. Okay, so if we look back and we look at the definition of R, it's the square root of sigma x minus sigma y over 2 quantity squared plus tau x squared, or tau xy squared. So what do I have here? I have R squared over R, right? So that then simplifies to R. Nice. Sigma y prime is sigma x plus sigma y over 2 minus sigma x minus sigma y over 2. Now this is times the cosine of theta. So sigma x minus sigma y over 2r minus tau xy over r. What do I have here?
Average plus R or minus R.
Yes, thank you. I have the average minus r. So some pretty slick equations. So all that complicated stuff just becomes our average stress plus or minus this thing we call R, which is a function of our 3 stress components. Then we can look one more time at tau x prime y prime. That equation is tau xy times cosine of 2 theta. So we have sigma x minus sigma y over 2r plus sigma y minus sigma x over 2 times sine of 2 theta, which is tau xy over 2. What does that look like? Or what does it equal? I think I have a 2 there instead of an r. That should be an r.
Same thing, aren't they? Just double.
Are they double or are they opposite?
Does that equal 0?
It equals 0. Does everybody see that? In the first term, I have a sigma x minus sigma y. In the second term, I have a sigma y minus sigma x. So those two are going to be the negative of each other, equal and opposite. Everything else is identical. Therefore, this is going to equal 0. So what we've just found is a pretty profound finding about this principal plane. What we've decided is that there is a plane called the principal plane. We get there by rotating theta p degrees. And when we get to that orientation, we have a principal stress that is equal to sigma average plus r. We have another principal normal stress that is sigma average minus r. And we have tau x prime y prime equal to 0. So your principal plane is the plane on which you have 0 shear stress. You only have normal stresses on your principal plane. And those normal stresses will be the average of your normal stresses in any orientation. If I give you any orientation and I tell you the sigma x and sigma y, if you take the average of those and add r, where r is the square root of sigma x minus sigma y over 2 quantity squared plus tau xy squared. If you calculate this, you'll always get what we call sigma 1 and sigma 2. Sigma 1 and sigma 2 are your principal stresses. sigma 1 is always greater than or equal to any sigma y prime or sigma x prime that you'll experience on any other orientation. And sigma 2 is always smaller, less than or equal to those. So as you rotate it around, the smallest stress, and when I say smallest, I mean most negative. If it's always in tension, then it would be the smallest magnitude. Well, it's always smallest magnitude. But just keep in mind that as you start to go into negative numbers to indicate compression, you're getting a number that is very negative. That's what I mean by small. The absolute value of it might be large, but it's the most negative. So the smallest number, smallest stress, or most negative stress you can ever experience given that loading is going to be your sigma 2, and your sigma 1 is the largest that you'll ever experience. And you see them on the same orientation, just on opposite sides, on perpendicular sides rather. And we get there by rotating it this many degrees. 1/2 inverse tangent of 2 tau xy over sigma x minus sigma y. And I'm going to put a little 1 here because actually there are 2 different rotations that give us the same state, right? If I told you that sigma 1 and sigma 2 are acting on 2 opposite sides. Let's see, this is sigma 1 and sigma 2. If I rotate that another 90 degrees, I'm going to get the same stress state, right? It's just the side that used to have sigma 1 is now rotated to have sigma 2. So what that means is we have a second theta P2 is equal to theta P1 plus pi over 2. These are all in radians. So we started with some stress state that had sigma x, sigma y, and tau xy. We rotated it by either theta P1 or theta P2, and it took us to this new stress state where we only have normal stresses. And these normal stresses happen to be the largest and smallest normal stresses we will ever experience at any orientation. What part of this do you want clarified?
When you say sigma average, what does that mean? Is it just...
Sigma average means starting with this stress state, I take sigma x plus sigma y and divide by 2. And sigma average is actually what we call an invariant, which means it's a constant regardless of our orientation. So if I were to look at this same stress state at any rotation, whatever my sigma x prime and sigma y prime values are, I could always take the average of them and get the same number.
So that sigma average isn't like force over area?
No. Thank you for clarifying that. No, we do talk about average stress when we're talking about calculating these stress components. So when I talk about sigma average previously, I was saying, for example, if you have an axially loaded member, like we pull on the ends of this, that would be our force divided by the cross-sectional area of this object. That gives you an average stress component. But now when I say sigma, or when I say average, I'm saying average of these 2 stress components that we've already calculated. Thank you for clarifying that. Other things that are a little bit muddy? Okay, so another big question we might be asking ourselves is what angles of rotations maximize or minimize the shear stress? How do you think we figured this out? Yeah, do the same thing, take the derivative, but now instead of taking the derivative of sigma x prime, we'll take the derivative of tau x prime y prime. Good. So that means we take the derivative tau x prime y prime with respect to theta. And when we do that, we get negative sigma x minus sigma y over 2 times 2 cosine 2 theta plus tau xy times negative 2 sine 2 theta. And of course, that equals 0. So now when I solve, I end up with a very similar but slightly different answer. I get that the cotangent of 2 theta is tau xy over negative sigma x minus sigma y over 2. So instead of it being tangent, it's cotangent. But previously, I said from our other derivation that the tangent of 2 theta equaled tau xy over sigma x over y over 2. So I have tangent of 2 theta, and actually we gave that a special name, theta p. So tangent of 2 theta p looks identical to this new cotangent term except negative, right? They're equal and opposite. So I can say that the cotangent of 2 theta is equal to the negative tangent of 2 theta p. And now to make it a little bit less confusing, I'm going to give this one a subscript s. So that way we know which theta is which. In order for this to be mathematically true, 2 theta s must be equal to 2 theta p plus pi over 2. That it just has to be in order for the cotangent of that angle to equal the negative tangent of the other angle. Which means that theta s equals theta p plus pi over 4. So what we're saying is that the principal plane and this plane that contains the maximum shear stress are oriented 45 degrees away from each other.
I'm not sure if I didn't really get how we got cotangent to theta s.
How we got this term?
No, the one, I mean, it says, yeah, you got it like as negative tangent to theta.
Yes. So previously we had, on a previous slide, we had written this. And so what I'm saying is if that is equal to tau xy over sigma x minus sigma y over 2, and this is equal to tau xy over negative sigma x minus sigma y over 2, one is the negative of the other. And so I have that equality. Other questions? Okay, so the big find here is that the orientation is 45 degrees from the principal plane. So now, just like we did before, we can figure out the magnitudes of our stresses on this shear plane. And to do that, I'm going to make this triangle like I did before, except now I'm dealing with the cotangent of 2 theta being tau xy over negative sigma x minus sigma y over 2. Because it's cotangent, it's now adjacent over opposite. So I have my tau xy on the bottom instead of on the side. And so R is going to be equal to the square root of negative sigma x minus sigma y over 2 quantity squared plus tau xy squared. Is this going to be the same or different than the R we had before?
Is it negative sign?
There is a negative sign. Exactly, but that negative sign is getting squared. So in terms of the end result, it's going to be the same. So this is the same R that we dealt with earlier. Now for the cosine of 2 theta, it is tau xy over R. And for the sine of 2 theta, it is negative sigma x minus sigma y over 2R. So we'll plug these in to our equations. So we'll start with our sigma x prime y prime equation. That's negative sigma x minus sigma y over 2 times negative sigma x minus sigma y over 2R plus tau xy over R. All right. Take some time to look at that carefully. Let me know what that equals. Maybe flip back to your previous slide. What do you think?
Is that just R?
Yes, it is just R. It is. Oh, I've made this math. R. There we go. Right? It's R squared over R, which is R. So what this says is that that thing that I called R that seemed somewhat trivial at first is actually the magnitude of our maximum shear stress. Okay, we can come in here and calculate sigma x prime, which is sigma x plus sigma y over 2 plus sigma x minus sigma y over 2 times tau xy over R plus tau xy times negative sigma x minus sigma y all over 2R. Oh my. Okay.
In the previous slide, was that sine square of 2 theta?
On this slide,
Yeah.
ask your question one more time.
Is that sine square of 2 theta? Or?
No. I don't know what that is. That's a little bit too much excitement. There we go.
What is this plane called?
Maximum shear plane.
Does it have a name? Principal plane?
No, it's just the maximum. No, its name is what it is. Yeah. Although in this class we could call it the Matthew plane if you'd like.
Sounds good.
All right. So what is this equal to? This sigma x prime. Just the first term. Those second two terms negate each other. Excellent. And because I'm losing interest and you're probably losing interest, sigma y prime is also equal to sigma average. I could write it all out, but those second and third terms are going to negate each other again, and we're going to find that they're equal to the average. So a very important thing to remember. On the principal plane, bless you, on the principal plane, we have our maximum and minimum normal stresses, and our shear stress is 0. You cannot just reverse that on your maximum shear plane, right? Don't fall into the trap of thinking that your normal stresses are 0 on your maximum shear plane. They are equal to that average value. So another important point is that you have these two shear planes that are rotated 90 degrees from each other. Because if every time you have a principal plane, you have a shear plane 45 degrees farther, and you have two principal planes, you must then have two shear planes, and they must be 90 degrees away from each other. So what that says is on one of them, you're going to have a negative R. That's going to be the smallest shear stress that you ever experience. And on one of them, you will have a positive R. So the sign of the shear is switching just because we're switching our coordinate system. So based on our nomenclature for what direction the arrows go when they're positive or negative, the arrows are not actually changing. It's just where we're putting our X and Y axes is changing. And so it's flipping back and forth between positive and negative every time we rotate it 90 degrees. And so at any orientation, your shear stress has to be somewhere between plus or minus R.
And R is the maximum shear stress.
Maximum shear stress.
Stress.
Yeah. So say we started with some cube of material, and that cube of material had sigma X acting on it. It had sigma Y acting on it. And it had tau XY. What I'm saying is that if we rotate this to the maximum shear plane or the Matthew plane, what our stress state will look like sigma average, and then some shear stress with a magnitude of R, or negative R, depending. Yes.
So this entire thing that we've been doing is just to put it on a plane where we're getting our maximum stresses.
Yes. Yes, I could have done this lecture in 2 slides, and I could have just given you these formulas. But I have this pedagogical theory that if I explain where it comes from, you will remember it better. I don't know if that's true, but I think it to be true. Oh, I'm a true. Okay, so I'm running out of battery. So essentially what I want you to remember from this lecture is the equations that we got at the end. So here I want you to remember that on the maximum shear plane, tau xy is given by R, and sigma x and sigma y are the average, where R is equal to the square root of sigma x minus sigma y over 2, quantity squared, plus tau xy over 2, or sorry, tau xy squared. I want you to know that equation for R. I want you to know that that's equal to the shear stress on this plane. I want you to know that the average, meaning sigma x plus sigma y over 2, gives you your normal stresses on this plane. I also want you to know that when we're talking about our principal plane, the normal stresses are sigma average plus R and sigma average minus R, and your shear stress is 0. Those are the 6 things, maybe 7 if you count R separately, that I want you to know from today's lecture. All right, so with our remaining time, let's take a look at what this looks like in practice.
And R is different for both, right?
R is always the same. There was that negative sign that snuck into the equation,
Yeah.
but it's going to get squared anyway, so it's going to, you can just leave that negative sign out. Okay, so if we have, say, That's terrible. Some member like this, and that member is acted on by a force, like that. And we look at some little element in here, and we blow it up. Okay. What we're going to learn the rest of the semester is how to go from this statics problem to the stress components acting at that element, at that location. We haven't gotten there yet. So far, we don't know how to get these stress components. We're just learning what we can do with them once we get them. So we have this member acted on by a force, and I'm telling you that in there, this is going, if we look at a little material element, that little material element has stress components that are equal to 100 in the x direction, positive, 300 in the y direction, negative, and 200 positive tau xy. So if I assume this is x positive and this is y positive, a positive shear stress goes like this, where I have positive direction arrows on my positive faces and negative direction arrows on my negative faces. And that has a magnitude of 200. So that's the little stress state picture that we're looking at. So if we look at our equations for sigma x prime, oops. Okay. If we look at our equations for sigma x prime and sigma y prime and tau x prime, we're going to get some equations that look like this. Sigma x prime is equal to the average. What is the average of these two normal stresses? Perfect, negative 100. Plus, what happens when you take sigma x minus sigma y and divide by 2? Get 200. And then cosine of 2 theta plus tau xy, which happens to be 200 as well, sine of 2 theta. So that's our equation for tau, or for sigma x prime. For sigma y prime, we have the average, which is negative 100. But now, and we have the same equation, except we're going to have negative signs. So we have negative 200 cosine 2 theta minus 200 sine 2 theta. Now for tau x prime y prime. See our equation, I don't remember which term is which. Both of these are equal to 200. Let's see. Okay, so tau xy is multiplied by cosine 2 theta. So I'm going to start with my tau xy, which is 200 times cosine of 2 theta. And then I'm going to add the sigma x minus sigma y over 2, which also is 200, and then sine 2 theta. Okay, so those are your equations that give you your values of these three stress components for any rotation. And that's not what it asked us to find, but we're taking the long road there. So I'm going to, just for fun, I'm going to plot these. And if we look at sigma x, make that one the green. So if we look at sigma x prime, it at a value of theta equals 0, so this is theta. At a value of theta equals 0, it equals 100, right? It also equals, let's put 90, 180. It also equals 0. I'm sorry, it also equals 100 when you go to 45. And when you get to 180, it's going to equal 0 again. So what you're going to get, let me just double check. Is that right? That when you put 45 in, does that equal?
That's
I think it does. You can double check it if you want. But essentially you're going to get a curve that looks like that. Then we can look at sigma y prime. That one's going to start at negative 300. It's going to end at negative 300. And it's going to be the mirror of the equation that we just plotted. So they're going to look like this. Except, let me try that one more time. We'll have to settle for that. And then the last thing we're going to do is draw the tau xy. It starts at 200. It's going to peak at this point. It's going to end at 200. So it's going to look like that. So that's more or less what these look like. And so you can visually see as you go through this rotation of 180 degrees, there are some points of interest. One of them is this point. What do we call that point? It's where we have our minimum shear stress. What is that plane called? The principal plane is where we have our maximum shear stress. It's the Matthew plane. It's our maximum shear stress plane, right? And if you notice, the two normal stresses have the same magnitude at those points. That's where they're crossing over. And that magnitude should be equal to your average, that negative 100. The other plane of interest is this plane and that plane. What's that plane? That's your principal plane. That's where you have your maximum and your min normal stress and your zero shear stress. And then on the other principal plane, the two normal stresses flip places, but you still have zero shear stress. Cool? All right. So back to what this question asked of us. It said find the max and min stress in the primary and maximum shear planes. So the maximum and minimum stress we can find by first finding where these planes exist. So who has the equation for theta p?
2 tau x y.
Sigma x minus sigma y. Cool. So that's 1/2 inverse tangent of 400 over, is that over 400? Let's see. I think so. 100 minus a negative 300. What's the inverse tangent of 1? 45 degrees. Okay, so this is 22.5 degrees. And that means that theta s has to be 22.5 plus 45, or 67.5 degrees. And that should line up with what we saw here. Right here, right in the middle between the 0 and the 45 is where we had our maximum shear plane. Sorry, our maximum principal plane. And then another 45 degrees from that was our.
When doing on like tests or quizzes, do you want this, do you want it, the calculations in radians? Or do you?
It does actually not matter. I think I did say they were in radians, didn't I?
Yeah.
They were only in radians because I was writing pi over 2, and pi over 4. But if you convert that to degrees, you can do it in degrees. Yeah. So as long as you're consistent, you're fine. All right, so now we have our angles, 22.5 and 67.5 for theta p and theta s. Now we need to plug that into our equations. So for sigma x prime, we said it was negative 100. What did we say after that?
200 cosine.
Okay, so 2 times theta p would be 45. Sine 45. Okay, what do you get for that?
$182.
182? What do you get?
182.84.
We'll say 183. And it's positive?
Yeah.
Perfect. Okay. Theta y prime was negative 100 minus 200 cosine 45 minus 200 sine 45. Can we get a number on that?
I was thinking we were gonna use the ones that we call.
We can use that.
But if you have to calculate the angle of the planes, you kind of want to use the arc. Because they don't have the angle. Because then you just go back and use the angle, right?
So there are 2 different ways to get to the same end place. So we'll, if I get a number here, then I can show you the other way using the R, and we'll get the same values. All right, negative 3 at 3. Okay, so if we aren't interested in the orientation, we're just interested in the magnitudes, we could skip to sigma 1 being sigma average, which was negative 100 plus R. So R being 100 minus 300, which is, sorry, 100 minus a negative 300. So that's a positive 400 over 2 quantity squared plus tau x prime y prime quantity squared. What do you get when you do that math? 183. So notice that when I did it using the actual function for transformation, I got these two values, positive 183 and negative 383. When I calculate sigma 1, which is our maximum stress, I get the 183, which corresponds to our sigma x prime, that's our highest value. If I do sigma 2, where I take the average minus r, I'm going to end up with this negative 383. And so r must be 283, which that is equal to our tau max, which happens on this shear plane. You can also get that number by plugging in the 67.5 into this equation. So you can do it either way. But this is probably, well, this is the faster way. But if you need to know, if it's important to the problem to know which of your two components is sigma 1 and which is sigma 2, right? Whether this is sigma 1 or that's sigma 1, you may need to do a transformation equation to really get that.